So we continue our discussion on multi-objective problems in material selection. What we have seen lastly is that using methods what we refer to as the trade-off surface method, we are able to plot the two indices which are having different units. Like we are plotting, we have seen that lastly we saw this example where you are plotting the price of a bicycle versus the mass of a bicycle. We have seen that the solutions which give us less price, they give you high mass, and the solutions which give us less mass, their price is high. And that is why we need to have those solutions which are a compromise in between these two, and then obviously those solutions that we may arrive at, they may not be optimum by any of the metric, neither optimum by the price metric, neither optimum by the mass metric. They may be somewhere midway here. So there are a number of solutions, and we have seen established lastly that the solutions which lie on the trade-off surface or which are near to the trade-off surface, they are better than the solutions which are away from the trade-off surface, which tells me that the solutions which are sorry, which tells me that the solutions which are located here near to the trade-off surface, they are better than the solutions which are here, which are available here. So these solutions which you see here, they are referred to as the dominated solutions, and the solutions which are near this surface, they are referred to as the non-dominated solutions. The question which we are not able to answer till now is that whether I shall select these dots, whether select a solution here which is available on the trade-off surface, or a solution here with this yellow one, or a surface here, or a solution here. All of them are viable. Which one is to be selected, that is yet to be answered, and we will try to answer that through going into the details of what we refer to as the trade-off surface method. So going forward, we find that using the trade-off surface only, there are a number of strategies, there are a number of sub-methods in which we can, by which we can select materials. So one of them happens to be by the experience itself. So what we do here, that you create a trade-off plot between the two metrics. One of them, let us say, was the cost, and here was the mass. We create a trade-off plot, and obviously there are a number of solutions, the red color ones shown here, which are near to the trade-off plot. They are all suitable solutions as compared to the other ones which are available as the gray dots here. Now, suppose we understand that right now I have a solution here, that is the material which I am using for making a product is this one. It is having a very less cost, but the mass is very, very high. Now, using intuition itself, I will be able to decide, I can decide actually whether I want to replace this currently used material by a material here which is midway, or whether I want to select a material here which is too far away from this one. Now, this selection in replacement of the current material with these materials actually is based only upon purely upon the experience without any mathematical calculations here, and that is why we say that we can select any of them accordingly. The basic reasoning will be that the choice will depend upon how highly you value a lightweight. Obviously, a question which is answered by the experience means, in simple words, which I want to say is that I have a component which has a very less cost and the mass is very high. I want to create a less mass component, but the cost is then increasing. Now, whether it will be feasible to have a value addition to the product so that it will be still sellable by reducing the mass and increasing the cost, then how much? Whether I can shift from this current material to exactly to this material, will it be sellable, or I need to settle down for somewhere in between? Now, that is an application oriented answer. If I may be able to sell even a material component made of a material which is available here, it may be having very high cost, but still it may be sellable, or in certain cases I may not be able to do that. But we are saying that the first way we do it is just by experience, and I say just upon the intuition or experience I can select any of them, and the selection will vary from person to person. Okay. The second method, the second way to do that is that we may reformulate one of the objectives as a constraint. So we are seeing here that we are plotting the two objectives here, the cost objective and the mass objective. We can say that I will use one of the objectives as a constraint. What I mean to say is, let us say that I will say that, okay, I say now that the mass of the product that you made by using this material here must not be more than 11 kilograms. It may be a bicycle itself. So I say that I want to select a material or a bicycle for which the mass is a limit. It cannot be more than 11 kilograms. So I say now the gray portion is reduced. I will remove them. So I am only left with this now 5 or 6 solutions. Similarly, if I say the mass shall be even less than 8 kilograms, so I may put a line here, and then many of the solutions will be reduced. But this still is not an optimization method. We are just converting one of the objectives into a constraint. So the mass objective has been put into a constraint. If I use the second objective also, if I put a constraint upon that, so I say the mass shall not be more than 11 kilograms and the cost shall not be more than $200. Then I am actually I'm opting out for these materials 1, 2, 3, 4, 5. They are out of selection criteria, and this box shape region is then left there, which will be that region in which the probable candidates are available to me, and then obviously I can either select this one or this one. Other ones are removed. But this is based upon just your, what we say, a method in which one of the objectives is converted into a constraint. Precisely. So we say you can have an optimum solution. So I already told you that mass versus price of a bicycle, you can create a box shape region by formulating one of the objectives as a constraint, and then maybe the second one also can be taken care of by something. And now we find here that this box shape region is giving us that region in which the solutions are available, and we have screened out the other solutions which lie outside this box region. So these solutions which are lying here, they are removed, and the solutions which are available to us in this gray region, they are also removed. So this is another way of doing that. But there may be a better way available, which we'll be talking about later as the value function method or the exchange constant method. But before going to that, let us talk about one case study. It's a very interesting case study. We want to select. What we want to select? We want to select the material for making bottles which are used for storing carbonated water or maybe soft drink bottles. So we want to select a material. Now, if you have read through the eco selection notes which I have provided you earlier, and you may have read about that, what do you mean by the terms which are listed here? The embodied energy, what is the manufacturing energy, what is the storage energy required to transport. These are all things which you have read in those notes. And similarly, we talk about the eco audit, and then we say that this is some eco audit plots, output of the eco audits, which tells me that over the life cycle of the product, which in this case happens to be a soft drink bottle, how much energy is consumed. So we have seen already that suppose this bottle that you are seeing here is made up of PET, polyethylene terephthalate. The cap of the bottle is made of polypropylene. It is actually then transported from the manufacturing base by around 500 kilometers to the selling base. It is stored there in a refrigerator for 2 days before selling it to the customer, and then it is recycled. This is a complete life cycle which we have read in the life cycle analysis. Accordingly, what we know from data is that the embodied energy. Now, what is embodied energy? If you recall, embodied energy of, if it is written as PET or any material, is the energy consumed to create 1 kilogram of material. So if I say embodied energy of PET happens to be 84 megajoule per kilogram, which simply means that to create 1 kilogram of PET granules, 84 megajoule of energy is consumed. Similarly, for polypropylene, it is around 95 megajoules per kilogram. Molding energy, because the granules will be then molded through a blow molding or injection molding process to form a bottle. So for molding 1 kilogram of polyethylene terephthalate or polypropylene, we can approximate that the molding energy happens to be nearly 19 megajoules per kilogram. And then the transportation energy, and that way we are able to find out that this is what looks like a bar chart, which tells me that how much energy is consumed during the various phases of life of a product. So the first phase of life is material. The second phase of the bottle is manufacturing, that is converting the granules of PET into a bottle. The third phase is and filling it also with a cold drink. And then third phase is transportation, that is from a factory it is transported by a truck to a restaurant. Then it is used there, means it is stored there for some time and then sold out and then disposed of and then obviously recycled. We already said it is recycled. What we see here is that the largest contribution to the energy here happens to be out of this material, means almost 350 megajoules of energy is consumed for making the material of these bottles for 100 bottles. The other parts are there, but it is less. So let us see, which tells me, it actually tells me that the largest contribution to the life energy comes out of the material. And if I want to reduce this total energy of the total life cycle of this bottle, the better answer will be achieved if I am able to attack this area. That is, the material replacement may be a better option instead of doing some modifications here, because even a small modification or a small reduction in the energy consumed during the material phase by replacement of a material, let's say, will be actually contributing a lot to the complete one, because it is a large amount of, in percentage terms, it is very large amount. So let us consider a material selection problem where our objectives are two. There are two objectives. So similar to our last discussion, that is a multi-objective problem. The multi-objective problem is, the first objective happens to be that we need to minimize the life energy of a bottle. This total energy of the bottle must be less, means the embodied energy of the material plus embodied energy of the molding plus maybe refrigeration plus recycle plus transportation, it shall be less. That means actually the bottle that you are making here must be environment friendly. It shall be able to hold the drink and sustain the pressure, because a carbonated drink, the pressure inside the bottle is slightly higher than the atmosphere, and that is why the bottle need to be designed for sustaining that pressure. And the second objective happens to be minimization of cost. That is the underlying thing here, because for these kind of items, the minimization of cost is the biggest challenge. That I want a material which shall be used for making this bottle, it shall be environment friendly also, as well as the cost of the bottle also shall be very, very less. So that is where the conflict will come, and we will try to solve it using the trade-off surface method. So let us solve this problem. So we see, we translate this problem. When we translate this problem here, the function is, it is a drink container. The objectives which I have highlighted here, that there are two objectives here. Minimum embodied energy per unit capacity, means the embodied energy of this bottle for this containing this unit amount of fluid or drink here must be minimized. And second is the cost of the bottle shall also be minimized with a constraint. So what are the constraints? So there are a number of constraints. The constraints are that it must contain the pressure inside it. So I can then design this bottle as a thin shell. It must be moldable. Whatever is the material, it must be moldable. Another important constraint here happens to be the material must be transparent or translucent. Means it will root out many of the materials out of our discussion. They will be screened out because they will not meet these constraints. Must be recyclable. So this last three constraints actually will actually screen out many of the probable candidates. Like metals will be out because they are not transparent. The polymers will be in because they are moldable. Polymers will be in because they are recyclable. Glass may be used because it is transparent as well as recyclable as well as moldable. So that is what we understand already, that putting constraints here is helping me to screen out maybe, let us say, metals. elastomers, ceramics, they are all ruled out because of these constraints which you are putting here. They may be able to fulfill the first constraint, satisfy the first constraint, but they will not fulfill the other three constraints. And the objective, as we said, the objectives are two, that it must have the minimum embodied energy, and second is the cost must be minimized. So let us design this bottle. This design, as I said, this bottle is designed on the basic thin shell theory, which tells me that there are two types of stresses, the circumferential stress and the hoop stress, which are given as PR upon T and PR upon 2T. The higher one happens to be PR upon T, and we will decide the thickness of the bottle T as S times PR upon sigma y. S happens to be the factor of safety. P is the pressure, R is the radius, sigma y happens to be the yield strength. So it is nothing but that we are taking PR upon T here. Sigma is equal to PR upon T times S. So T happens to be S times PR upon sigma y. And if this T is established, that means it will give me the minimum wall thickness which is required to sustain some pressure P. Then we can actually calculate what is HA. HA happens to be now the embodied energy of the bottle. It now happens to be T, the thickness of the bottle, area into T into HM into rho. T into rho is the density, T is the thickness, and what is HM? Now HM is what? We say HM happens to be the embodied energy of the material of this bottle in megajoules per kilogram. So we say it is HM is embodied energy per kilogram. So HA, the total embodied energy of the bottle, happens to be thickness times HM times rho. So I substitute the value of T from here, and then I say that now this happens to be S into P into R, HM rho upon sigma y. So this is the expression for HA, and which we want to minimize. We want to minimize the embodied energy. For doing that, because S is constant, P is constant, R is constant, we say H will be minimized, which if HM rho upon sigma y is minimized. So I take that the first index or the first parameter here which has to be minimized here for first performance metric for your first objective, which is minimization of embodied energy, happens to be HM rho upon sigma y, where HM happens to be the embodied energy of the material per kilogram. So M1 is given. Similarly, now for the second objective, which was for minimization of cost. So we have now the second objective for minimization of cost, and it resembles to what we have already seen in our discussion, that at M2, the metric or the index for this case happens to be now, or minimization of mass happens to be Cm rho upon sigma y, and Cm is the cost of material per unit mass. So I have two indices now, two performance metric, which we'll try to solve using what we call as the trade-off plot method. And in this trade-off plot method, each objective is defined by a performance metric. The first objective of minimization of embodied energy is defined by M1, and the second objective for minimization of cost is given by M2. So I have two indices or performance matrices M1 and M2, which gives me that if I am able to minimize, obviously now you recall that we are talking about minimization of the indices, and that is why if I am able to minimize HM rho upon sigma y, the embodied energy will be minimized. If I am able to minimize Cm rho upon sigma y, the cost will be minimized. The problem is, obviously, there is a conflict. The choice that optimizes the embodied energy, it may not optimize cost, or the one which minimizes embodied energy, it may not have the minimum cost. And a material which has the minimum cost, it may not have the minimum embodied energy, and that is why we have a conflict. Let us look at a solution of this conflict and try to find out which is the most suitable material using the trade-off plot method, and I will use the EduPack software for plotting these material indices using its advanced plotting function. So what we see here is that before going to the EduPack solution, this is what you get from the textbook. That what it is a plot between embodied energy index M1. What was M1? Sorry. What was M1? The M1 is HM rho upon sigma y, and M2 is Cm rho upon sigma y. So what we have done, we have plotted the embodied energy index M1, that is HM rho upon sigma y, versus the cost index, that is Cm rho upon sigma y. And once you do that, because we have removed many of the materials like metals because of the constraints of moldability, transparency, or translucency, and recycling. That is why what we are able to plot, we are actually plotting most of the polymers. We have polyethylene, polypropylene, PVC, PET, PLA, glass is there. So what we observe, and then we create a trade-off plot. So this trade-off plot is then created. So we have plotted the index 1 here on y-axis, index 2 is created on x-axis, and then we create a trade-off plot. From our understanding of the trade-off plot method, we already know that the solutions which are available to us, which are near to the trade-off surface, that is this solution and this solution, they are the better solutions than the solutions which are available here. Which simply tells me that why now bottles are made of PET, because we see that PET happens to be very near to the trade-off surface. Another viable solution is PLA, polylactate acid or polylactide. For PET, we understand that the cost is actually the minimum. If I compare PET with all these, the cost index is minimized, is optimized. So PET is optimum for cost, not that optimum for embodied energy. It uses higher embodied energy. When I look at another material, PLA, polylactide or polylactate acid, which is a biopolymer, we understand that it is optimizing the embodied energy, but the cost of PLA is higher than PET. So it is on a higher scale. It is not minimizing the cost. It is minimizing maybe the embodied energy. So a bottle made of PET will be still less costly, slightly more harmful to the environment than a bottle made of PLA. Glass, if you see that, glass, we understand the cost of the glass is still higher, and the embodied energy is actually less than PET because glass is recyclable. We can refill the bottle again and again. But there are limitations of glass which will be not going into this case study. But right now we are just plotting various materials on a trade-off surface and then trying to visualize that what is the solution. Now, let us look at that what we observe in EduPack. So the same thing plotted on a EduPack software. What we have done now, I am now plotting the first index which you derived as HM rho upon sigma y, and second index CM rho upon sigma y on x-axis and HM rho upon sigma y upon the y-axis. Keep in mind we are using the log scale on the y-axis as well as on the x-axis. So we are plotting the index 1 directly using the advanced function and index 2 directly using the advanced function. And then we plot this orange colored line is actually the trade-off plot. This trade-off plot actually tells me the answer is actually the solution is given. So I have this red one which we say is PET. So it happens to be the least expensive. So if you want to make a cold drink bottle, the one which will be least expensive will be made of PET, and that is true, and that is actually why almost all the drink bottles, cold drink bottles, are made of PET because they cost less. If you want to go for a solution which is more environment friendly, then obviously PLA, polylactide or polylactate acid may be a better solution, but the cost will increase. So the cost will increase here, but the environmental impact in terms of the embodied energy will be very, very less as compared to even PET. So this is the choice, the PLA is the choice for the lowest embodied energy. So which one I select? Either I select here or here, both of them are viable. I may still go for this. If there are changes further, now whether I select this one or this one, a scientific method is given by what we refer to as the exchange constant method, which comes later. But right now we say that based upon our experience, we can select that, okay, I will keep on making the bottle out of PET because that is the cheapest one and still environment friendly, not that damaging to the environment. This material, as we understand, is very good than the material available here, even a material here, the orange one, we say is polystyrene. So polystyrene is costing you more, the cost index is high, and the environmental impact is also high. So polystyrene is not a viable solution. Polyethylene, this one, the cyan colored one, it is having a higher cost as well as a higher environmental impact as compared to PET, and that is why this cyan one and this orange one that you see as polystyrene, polyethylene, they are not a viable solutions. PET happens to be a more viable solution PLA happens to be further a viable solution if the metric of environmental impact in terms of minimization of embodied energy has to be minimized. Okay, what happens if you consider glass also? So if you see glass now and plot glass also in our chart, this is what changes now. We understand that the glass comes here, the soda lime glass is here. So the glass is even using a lower energy, but again the cost is increasing. So the lowest cost index is for PLA. The lowest cost index is for PET. PLA happens to be costlier than PET. The glass happens to be further costlier than that, but the environmental impact of glass is further less. Costing is obviously now you can tell that costing is the basic reason why what is governing our selection till today, that we are making the cold drink bottles using PET only because it is actually able to minimize the cost with a certain level of environmental impact. It's not very environmental, harmful also. It is harmful than PLA, but still not as harmful as other solutions which are available here, and that is why PET happens to be a viable solution. This was one case study that we see that which tells me that how we can use the trade-off plot method to finding out materials in the case of multi-objective optimization. Here the case was that you wanted to have a material selection which gives you a material which is having less environmental impact as well as the less cost. Okay, thank you.